Good afternoon, everyone. My name is Ryan Lowe. Thank you. I'm here with my coworker, John Cesario, and we're here to talk today about capacity planning. John and I both work on the platform engineering team at Square, where we manage thousands of instances of MySQL, Redis, and other data stores. We find ourselves dealing with capacity planning almost a daily basis in the context of outages, performance problems, budgeting, and long-term planning. And the purpose of our talk here today is sort of to share with you some of the effective ways that we do capacity planning without making it our full-time job. And this won't specifically be about MySQL or any database, but we will sometimes use it as examples. We have 50 minutes today, so we're going to try to keep the talk around 35-40 minutes. So we have 10-15 minutes of questions at the end. But if you have a question during, please feel free to raise your hand or shout over me so we can be sure to get all of the questions answered. So let's start off by defining what capacity planning is. Per Wikipedia, the formal definition is the process of determining production capacity needed by an organization to meet changing demands for its products. A more pragmatic definition, however, is just knowing in advance when your site's going to fall over. And capacity planning is important to organizations like Square because, for example, once a single service suffered increased latency and in turn took down many other downstream services in a cascading failure situation. And the reason that it fell over was actually something that we knew would happen. We predicted it. We just didn't act on the prediction. And of course, we're here at the Percona conference, so I think everybody in this room has suffered an outage due to some disk space issues. Another common thing we've probably all seen at some point is running out of CPU or I/O capacity during peak load. And these are the things that drive us to capacity plan. The common denominator is always some exhaustion of some physical resources somewhere that costs money. There are, of course, software bottlenecks like mutexes, locks, IPC, and process overhead. But at the end of the day, we're dealing with finite physical resources located somewhere in the data center that have to be purchased with money. And by analyzing their usage and applying basic prediction methods to them, you can save money and prevent downtime. So capacity planning might not make your application faster, but it will let you know what you have to buy to support it and when you have to buy it. It's also worth noting that an often ignored element into this later, but one of the highlights of truly great capacity planners is that their efforts also include financial cost-benefit analysis, so become self-justifying for the people that actually have to pay for the hardware. So let's start with a quick poll of the audience. All of us here capacity plan at some level. Raise your hand if you typically do your capacity planning as part of an outage post-mortem. All right, we got 3 honest people in the crowd. Now raise your hand if you do capacity planning frantically before an outage so that you can hopefully find out what's wrong and if you can stave off impending doom. A couple more. All right, now raise your hand if you've got a PhD in mathematics and you're just here for the free Wi-Fi. All right, we got 2. So we'll have some fun things to share with you today, I think. Whenever we do capacity planning, we generally do it in the context of a resource or a set of resources. And we're not going to cover, again, every possible thing because we'd have to cover far too many situations that occur within the application layer. Again, when we talk about resources, we mean things that have very real physical limits, as opposed to software-based limitations, things that can be fixed with a pull request. Specifically, we're going to talk about hardware components and then complex systems as a whole. So let's walk through systems you should know. Working from the bottom up, we're going to talk about the space where you physically put your servers. Physical data center constraints are things like power, HVAC, physical space, or even weight. But if you're 100% cloud-based, you might not have power or HVAC issues, but you might have capacity issues when you can't allocate new instances in a specific availability zone. Remember, the cloud is just somebody else's computer. They're still bound by physical constraints, and therefore, so are you. It's important to understand these constraints because oftentimes capacity management just becomes a shell game of balancing resources, and the ability to add or upgrade physical server constraints can be used to offset efficiencies higher in the stack. For example, many of you here have probably traded memory for I/O or vice versa via the NODB buffer pool. So at many points in my career, I've been tasked with projecting or budgeting hardware purchases for my team. And one of the more unfortunate experiences I had once is we got a new shipment of racks. We plugged them in, set them up, installed everything, and realized shortly thereafter, during an outage, that the new CPUs consumed more power than the old ones. So our racks didn't have enough power to supply. So the outage itself wasn't particularly painful. What was really painful is the remedy. So we had to redo all of our density cost models and then work with a whole bunch of different teams to physically move servers from one rack to the other so that we would reduce power consumption per rack. So what's the point? Physical data center constraints do matter, and they can significantly impact the bottom line. Next is processing power. It's your total compute capacity. There's a lot of differences out there, but for the most part, most of you are going to be using x86, probably Intel. The important things to remember while doing capacity planning are the number of physical threads, the number of logical threads, and CPU speed. To bring this specifically into database land, most of us know that MySQL will scale to about 24 cores and no more. So CPU throughput is going to be much more important than a very high number of cores to get the most out of your MySQL systems. At Square, we provide a number of different SKUs for hardware. We do try to limit hardware variation, but new CPUs come on the market, old ones get end of life, so we sometimes add to the supported hardware collection. Well, in the not too distant past, we had a bug in our automation framework that allowed MySQL replicas to be provisioned with not the exact same CPU as every other member of the cluster. So over time, this resulted in the master having a CPU that was 20% faster than any of the other slaves in the cluster. And so features were added, deploys happened, traffic increased, and when we failed over to a slave that had a CPU that was 20% slower, it caused cascading failures with service timeouts. And so CPU speed is really important, especially if you run hot or close to capacity. And this is also why compute speed are bought in abstract units in the cloud. But it's still important to understand the underlying hardware because it can have major and minor version differences even within a single CPU family. Disk subsystems, they're interesting because they add a completely new aspect to capacity planning. When we talk about stateless services, we can usually assign a somewhat static high watermark for memory usage, which leaves CPU as really the only volatile resource. But disks add a couple of extra axes to the model. This is because media type can come into play when determining the maximum number of IOPS. Things like NAND versus spindle, BBUs, controller thread count, and a myriad of other factors can greatly impact the number of IOPS that are realistically available to your application. And you can't measure disk capacity by IOPS alone because due to differing media bus types and workloads, not all I/O operations are created equally. And of course, disk space. So the two primary characteristics of disks for capacity planning, IOPS and storage capacity. I once talked to a SAN vendor that reported millions of IOPS. Right? And this was a theoretical number, and what the vendor failed to mention was that this performance came at the expense of durability for the SAN. And this isn't only large products either, right? Everybody knows Intel SSDs. They're a great product, but one thing to note is the difference between the 500 series and the 300 series is that the 500 doesn't have enough internal power capacity to flush the buffer completely to the physical media in the event of a power outage or failure. So disks add a lot of complexity to the capacity model. Network capacity. So once I managed an application that served web ads. It was a great product. It was great design. The data set was only in the tens of gigs, so we had a buffer pool that was 150% of the data set size. It was super happy, chugged along all day, doing its thing without issue, until one day we got DOSed. Now MySQL, of course, happily kept doing its job until it suddenly started showing all of the signs of typical resource exhaustion, right? High volatility for threads running, massive spikes in latency, and it took us a while to figure out because both I/O and CPU had plenty of headroom left. It turned out we had saturated the network. And this was back in the days when 10base-T was the standard, and nowadays you're far less likely to do it. But even as recently as last year, I've seen it happen in production. So it's important to understand that the network is just another resource that eventually ends up as a physical device that has an associated cost. When considering memory, the two primary considerations are speed and the capacity. Real quick, before we move on, memory can have multi-channel setups, and these type of setups increase the amount of bandwidth available to a space in memory by allowing the bandwidth from multiple sticks to be used in unison, and that can be really important. So we won't go too deep into details because most applications aren't going to make use of the kind of bandwidth provided by 2 or more 64-bit channels. But what this means is that to take advantage of that speed, you have to have like multiples of 2, 4, or 6 of the same SKU, but it differs per hardware vendor. And the point of this is that if you have one node with one single 250 gig stick of RAM and another node with 4 64 gig sticks of RAM, they're going to have different performance characteristics because they're going to have different speeds. So it's just important to know when you're planning exactly that you have the same physical hardware that you're planning for. So we're at a database conference. We would be remiss if we didn't at least mention database-specific resources. So whether we're talking about the InnoDB buffer pool, thread cache, or even the query cache, these are virtual resources that artificially limit system scalability, so we won't really cover them here. But in addition to the physical resources mentioned above, there are also virtualized resources or complex systems that stand alone. And this is important as we move into a microservices-oriented architecture that you understand the SLAs and resources provided by your vendors. This is because your SLAs will only ever be as good as the SLA, as the worst SLA among your chain of resources in your application stack. And this even includes the SLA on things like the diesel generator in your data center. So in the new cloudy world of services, you might encounter third-party resources that have explicit rate limiting or throttling and different, based on how much you pay. So these need to be taken into account when you're doing capacity planning as well. And we'll walk through modeling this a little bit later on. So it's just important to understand service relationships, service SLAs, service capabilities, and failure scenarios when you're doing capacity planning. Looking at the diagram, we can see that the actual public endpoint for the application requires a myriad of interdependent services. And the important takeaway is that the bottleneck might not easily be apparent in more complicated architectures. And the worst SLA, again, among all the services is going to be the one that's the gating factor for your customers. Real quick, performance operations on hardware components. This graph is probably familiar to most of you. It shows the order of magnitude difference in latency between various operations. It doesn't really do it justice here because if you notice the y-axis, we're scaling logarithmically, so the difference is much greater than what's displayed here. So we start with a single CPU operation, which takes approximately 1 nanosecond in modern CPUs, and end with an ICMP ping from California to Australia that takes 150 milliseconds. What this means in terms of capacity planning is that if you spend thousands of dollars on better CPUs, you can get an order of magnitude more capacity than spending that money on memory, and then you can get hundreds of times more capacity than by spending money on disk. So if you model an application that can do X requests over Y time, but you know that the main bottleneck is IOPS, you know that you can probably get more capacity by adding disks, and that's a simple solution. But if you spend time to refactor that application to not need so much disk and put more of your data directly in the CPU cache or in main memory, then you can get orders of magnitude more performance. But of course, it's a trade-off, right? You're spending that time, engineering time, just for capacity, or you could spend the engineering time building new features and making more money. So John and I have both spent time at a lot of companies, both big and small. We've experienced capacity planning at all stages. For example, if you're 2 people in a garage, you don't really need to have a strong capacity model because if you can't ship a product, it won't matter. In the early stage of a company, there's usually little to no capacity planning, and this is totally appropriate for a company of that size. Next, you probably move into reactive capacity planning. So continuing with the startup analogy, you've got some customers, some of them might even pay you, then the site goes down and starts throwing 500s. And this is the stage where you experience the pain from lack of capacity planning. And they usually react by just throwing money at the situation. And this is fine for a company of that size, right? You're still trying to keep the lights on, and engineering hours are better spent writing new features and making money than, or you can just spend a couple $1,000s and improve some subsystem in your stack. So again, it's not, throwing money is not a bad thing. One of the things early on we had at Square is we had an I/O capacity issue. We had IOPS, not disk space. So the long-term solution of this monolith was of course, break it into microservices and distribute the load equally among many computers. But at the time, we just threw money at the problem, bought PCIe flashcards, and then that gave us years of runway so that we could slowly migrate away from the monolith. So it's a cost-benefit analysis. Our engineers could keep working on the good things, and we just dropped a couple bucks to solve the problem in the short term. And even if we could have broken the monolith up in, say 6 months, that would be 6 months where there's no feature development. So to make good business decisions and make good engineering decisions. Reactive capacity planning is a process not unlike the one described here by Calvin's dad. Wait till you hit your capacity and then formally document that as your limit. So here in the comic, we're looking at load limits on bridges. They just keep driving larger trucks on the bridge until it collapses, then they weigh the last truck and say that's the limit. Later on, your company's at a point where you decide to hire an expert. It might be somebody like Michael Finch, who's just been there, done this, seen this movie 1,000 times and know how it ends. We'll call this person Frank. Frank comes in, he takes a look at your system and does a quick design document, and he knows industry best practices, will probably save your company from a whole lot of capacity-related outages just by fighting for best practices like read-only replication slaves and low-hanging fruit for opportunities for improvement. So as you move on, Frank's done a lot of good, implemented a lot of standard practices, and now it's time to get a bit more formulaic about capacity planning. So there are two good things about the internet, right? Cat pictures and downloadable Excel spreadsheets that'll do capacity planning for you. Often, it's as easy as capturing some status variable over time and then plugging them into a spreadsheet that you downloaded and just wait for the graphs to be populated. So next, you might start using benchmark to create capacity models, and a lot of people have love-hate relationship with benchmarks. You have to be aware of the right way and the wrong way to benchmark your applications. The right way is to not benchmark individual components like your web server and then your database, but rather to benchmark the entire stack from the same endpoint that your customer sees. And the reality is, unless you're benchmarking the exact same thing as your customer uses, you're going to fail to determine the weakest point in your stack. So you can use benchmarking to create high watermarks for application endpoints, and then that'll allow you to have a decent knowledge of at what point does the application start violating your SLAs. And one of the common failures that I often see during benchmarking is that they'll just scale up the workload till the system falls over, mark that point, walk away, and call it done. And that's not really useful. The more useful question to answer is, how many requests per second can you sustain without tipping over time, while reserving a safe amount for unexpected load and peaks, right? So what is n-1, where n is the number of your requests your application can take before it tips over? A few years ago, I was doing Redis benchmarking, and I let it run overnight. It turns out all of my benchmark experienced severe degradation at about the 18-hour mark. So there are plenty of apps where weak points are only found once various buffers and caches are saturated. So once you have this data, you need to find out, what's the worst bottleneck? Is it the database, the web server? And within that, which component is it? Is it the disk, CPU, virtual mutex, the network? These are questions that you need to ask. It's always fun to benchmark individual components, and it's also usually part of the hardware purchase process. And there's a place for component benchmarking, but it's important that you ask the right questions when you're evaluating hardware. We often buy hardware from vendors based on theoretical spec sheet numbers. Do your benchmarks prove or disprove the numbers that are given to you, because they're almost always done in unrealistic lab situations. Benchmarking is worthy of its own talk, and I think there might be a couple this year. So also look at your benchmark results as sort of your best case scenario. Most people today have some sort of trending system like Graphite. Most of the time it starts with somebody just spinning up an instance and putting metrics into it. These are rarely the right metrics, but over time, as you figure out what's important, you start to get really interesting metrics and a good picture of your system health. So once you have this, you actually have everything that you need to progress to a better way of doing things by applying some basic seasonal forecasting to your metrics, and we'll do that in a couple minutes, and predicting when you're going to run out of capacity. So it's at this point where you graduate from reactive planning to proactive capacity planning. And this usually works out to be very accurate, because most public customer endpoints do have some semblance of seasonal cycles. So you'll be able to authoritatively say, oh, we'll run out of disk space between July and August with a lot of certainty. So one of the first things I usually do when I start a new company is whip up a script to take Graphite data and just apply a basic Holt-Winters algorithm to figure out when we're going to predict outages and hopefully avoid them. Next is instrumentation. I don't mean things like New Relic, although New Relic is awesome. What's really interesting is to be able to observe the life of a request as it goes through your system. When it's done correctly, this is called isotopic logging, and it's designed to help you keep track of separate operations and their parts within the whole execution flow. For example, if every request is logged with a UUID, you can use your logs to see the life of a request. So you can examine each component as it processes a request from service to service, and then break the entire request down into an actual measurable amount of CPU, I/O, and memory consumed. So this then allows you to prioritize the lessons you learn in capacity planning to the slowest link. Finally, once your company hits Google scale, you can hire a team of PhDs to model your capacity because it's worth your time to spend $10 million capacity planning so that you'll save $100 million down the road. And we only have this slide here so we can say the vast majority of us will never get to this point. If you do find yourself at this point, your money is better spent taking some advanced capacity planning course or hiring people that know what they're doing. And even though math is hard, we are actually going to talk about some of the formula that you should know in order to get better at capacity planning, and John's going to dive into some laws and models.
Oh, thank you, Ryan. Is this on? Hi. Are you guys really doing your PhD in math? Is that really happening? Because that makes me a little nervous. Okay, I feel better now, a little more relaxed. So we were talking a lot about hardware here, and what we're trying to do is show you how these hardware components really impact capacity planning, which is really about cost analysis. Like if you add $500 worth of disk, how much money can your company make more than that, right? So think of it kind of like that. Let me get this fixed. Test. Is that working? Good. So we talked about the various components here, and then let's dive into some of the laws and models. First up, we have Amdahl's law, which gives the theoretical speed up in latency of the execution of a task at fixed workload that can be expected of a system whose resources are improved. So let's real quick read through this equation. The speed up of latency is the maximum theoretical speed up of the execution of the whole task. S is the speed up of the part of the task that benefits from improved resources. P is the proportion of execution time that the part benefiting from improved resources originally occupied. That was a lot of words. In plain English, the theoretical speed up is always limited by the part of the task that cannot benefit from improved concurrency, and I'll show a little example here. So this is a for loop, right? Does anybody see where it's going to be blocked? In this example, the code is executed to get the directory listing, and then each file is acted upon sequentially. Looking at the program holistically shows us that there is only one part of it that cannot be parallelized, and that is listing the files in the directory. So if we just execute it as is, it takes 10 units of time. If we parallelize it among 2 cores, it'll take 5 units of time. With 4 cores, 4 units of time. With 8 cores, it takes 3 units of time. But with 12 cores, it takes 2 units of time. Therefore, without actually improving the underlying code, the maximum amount of time savings we can achieve only by parallelization is going from 10 units of time to 2. This is another one of those really obvious rules that lots of people tend to overlook. And it ties back to hardware because you got to understand, like, again, logical CPU cores versus throughput, right? You want to know where your blockers are, where your artificial scalability limits are. Next up real quick is Little's Law. The more you get into capacity planning, the more likely you'll stumble on Little's Law, which is something you'll learn when you dive into the basics of queuing theory, which you should. In our line of work, almost everything is a queue. There's a lot of great resources for learning the basics of queuing theory, and it's worth your time to spend a few minutes to do that. Little's Law states that the average number of customers in a system over an interval is equal to their average arrival rate, multiplied by their average time in the system. Although this seems pretty basic, it's actually incredibly useful. Over the years, a corollary has been added that the average time in the system is equal to the average time in the queue, plus the average time it takes to receive service. The original law was appended to include startup and teardown time. We'll take a very contrived example right here. We're going to talk about grocery stores. So assume we have customers in a grocery store arriving at a rate of 10 per hour. So the 10 arrivals per hour. They spend 30 minutes in the store, or 0.5 hours. This means we should find the average number of customers in the store at any time to be 5. This is super useful for those of us designing complex systems because assuming we know the capacity of all of our queues, the holistic capacity of our application, we can forecast the maximum arrival rate we can support and when we should start thinking about either increasing the capacity of the queue or decreasing the amount of time spent in the system. So let's go through some more useful examples with computers. Apache has a configuration directive called max request workers, which sets the limit on the number of simultaneous requests that will be served. Any connection attempts over max request workers will be queued. So once a child process of Apache is freed up from servicing any other requests, it will service the next one in the queue. So assuming we have max request workers at 256 and each request takes half a second to service, we can simply plug those numbers into the formula. So we know that with a constant arrival rate and all other things remaining equal, we can handle 512 requests per second before falling over. Little's law is really important when talking about scaling system capacity. The next common formula we'll talk about is more about prediction rather than capacity, and that's Holt-Winters. People who have a little more of a math background than me, and luckily enough we don't have any PhDs in here, may know this as triple exponential smoothing, which was then improved to n exponential smoothing. Some folks at Vox Media did an excellent multi-part blog post about Holt-Winters forecasting, and we borrowed this chart from their blog because it really highlights seasonality and what Holt-Winters is good for. Holt-Winters is relevant when data is somewhat repetitive, weekly or seasonal. Originally, this was created to help predict shortages in labor and agriculture, but those same properties make it excellent for predicting OLTP workloads within like a time zone. Many of us have customer usage which ebbs and flows on daily, monthly, yearly cycles. And so when we dive down into the physical resources, such as I/O or CPU, we see that reflected there in the same way because it looks something like a sine wave. And such, this makes it a perfect application for Holt-Winters forecasting. The maths behind Holt-Winters are way beyond the scope of this talk, but us mortals can use it by importing the R or Python packages to do all the heavy lifting for us, and we'll show that later. It's great for short-term forecasting. So this is the best formula. This is the universal scalability model, sometimes referred to as the universal scalability law. And it is one of my favorite ways to do off-the-cuff forecasting because it is so easy. I mean, that looks easy, right? Everybody get that? It predicts a system's deviation from ideal scalability based on simple measurements that are easy to collect. And that's really the superpower. So you don't really need to do a lot of work to get data that is easy to plug into this. The n in the numerator represents concurrency, the alpha represents contention or queuing, and the beta models coherency delay, or the work that the system must perform to synchronize shared data, mutexes, caches, explicit locks, things like that. When the coherency delay is 0, it actually simplifies down to Amdahl's law, which we just talked about a few minutes ago. And another cool thing about it is if contention and coherency delay are 0, you get linear scalability, which is, all of us work with apps that just scale linearly, right? So basically, and what do I mean by that? That means both of those show systems which have no IPC or state keeping, right? So here's a real example. We measured some samples of throughput and concurrency on a MySQL box, transformed the data, performed a square regression against it, and then reversed the transformation to find the parameters to the model. It sounds harder than it is. We took questions and threads running from show global status. Part of our standard monitoring system captures these every 30 seconds. We then smoothed that out to a 5-minute interval so that we could easily and quickly input more than a full day's worth of metrics into the equation in order to get a better sampling of actual workload. According to this model, we expect the system to peak at 70,000 QPS and then gently trail off. Well, this is me telling you that it didn't work out that right. And so when you use the universal scalability model, it's best to think of it as a best case, plus or minus 20%. We noted empirically that with the system in question, we're able to only sustain a steady state of about 61,000 QPS without issue. When the system spikes above that, it works for a moment and then falls off a cliff. And we had query pileups, retry stampedes, and quickly degenerated much faster than this graph would indicate. However, given that it's generated with simple show global status output, it's incredibly accurate for what it is. I wanted to do a quick shout out to Baron at Vivid Cortex. When I do this kind of modeling, I usually use the CRAN USL R package. We'll talk about that as well. But Vivid Cortex is a downloadable Excel spreadsheet, right? And that's awesome. And you can just plug the numbers in and get it quickly done. The website's a great resource for white papers and ebooks about the USL, queuing theory, and capacity planning. Check those out and also take a look at their Go repo because there's also some great math packages in there as well. So let's do some practical examples. Prophet is a prediction library created by Facebook for use in R and Python. It works best with daily periodic data that has about 1 year of historical data. Prophet is robust to missing data, shifts in the trend, and large outliers. And we will show how good it is at that. It's simple to install. And we're going to just real quickly install Prophet using R and give an example of using it to forecast. We chose disk storage metrics because everyone has had that fill up on them. And I'm sure everyone would like to know how you can build a simple monitor to give you a heads up when the disk is going to reach threshold like 30 days in advance instead of like 2 hours. So quick screenshot of the R GUI on Mac. Just install from the Rlang website. If you're on another platform, I'm sure it's in your package management system somewhere. Just get yourself to the R shell. After that, we install the package. Also simple. Just issue the command install.package as Prophet, and everything should just work out okay. We load up the Prophet package into our current R session. You might need to CD around to find where your CSVs are. R has getWD and setWD to help you out with this. We need a data set. Everyone here knows you can dump to CSV format in Graphite, right? Just go to the Graphite URL and add format equals CSV into the query. Just make sure the first column and your eventual CSV is time and the second column is data. Here's an example of how you can inspect the contents of your variables in R. Tail is available as well. The input to Prophet is always a data frame with two columns, DS and Y. DS, or date stamp column, must contain a date or date time, and the Y column must be numeric and represents the measurements we wish to forecast. This just means that if you have a CSV, make sure the first row includes headers called DS and Y. And you can see a sample of that right here. So this is the actual CSV. Note the header row up top. Prophet works best if you use daily inputs as well, because you're trying to do a daily input of the recent year's worth of data. And if you are using a Graphite, there's a pretty easy way to consolidate metrics by daily values. The function is called summarize. The first argument is the series, the second is the time interval that you want to consolidate to, and the third is the function you apply to the values in that period. When we instantiate the Prophet object, there are a slew of variables we can use to control the fitting of the data. The defaults are fine for our purposes here. You can check out Prophet on GitHub and look in the docs folder for more examples. We tell it how far we want to predict into the future. And here you can see we dump the future out, and we have some dates in the actual future. The future looks good. And the predict method will assign each row in a future a predicted value, which it names y hat. If you pass in historical dates, it will provide an in-sample fit. The forecast object here is a new data frame that includes the y hat column with the forecast, as well as columns for components and uncertainty intervals. Now that we've created the forecast module, here's the moment of truth. Everyone likes pretty pictures, and here it is. Yay! You probably noticed the gap in the black dotted lines first. This is the plotting of the known time series. It has gaps because we had some missing data along with a massive drop in disk space. We actually wiped this server and reprovisioned it, and you can see that the time series is still pretty accurate. I just wanted to show this because Prophet is really good at working with even big blocks of null values in the middle of your time series and still doing a decent job of prediction. Check out, the blue line looks really great up there. I was worried about that. Notice how the confidence band gets larger, right? Obviously, it gets more uncertain the farther into the future you get. If you wanted to get some computer readable data rather than just pictures, there's a write.csv function as well. Check the R manual again. And next we'll work on USL and R. We talked a little bit earlier about the universal scalability law, and now we can show you how to plot that in R. Now, modeling isn't the easiest thing in the world, and this is going to show you how that when you're using large real-world data sets, it can be difficult to derive statistically valid results. When we talked about Amdahl and Little's law, we saw that apps will basically scale forever as long as there isn't any mutexes or contention. Unfortunately, we work with databases, and locking is what we do. So predicting scalability becomes a little more complex. First, load up the USL package in R. It's not perfect, and every time I'm forced to use it, I usually find it wanting because I find some terrible way it's trying to stop me from doing my job. But it's still pretty much the best one out there, and I couldn't really find anything else. Next, we load our CSV into the data frame. The major difference in this one is that we just row names equals null. What it really does is just add a numbered index to your rows in there, which is needed for the evaluations required by the USL package. Next, we plot QPS and threads running within the data frame we just created. The tilde is just shorthand for declaring X and Y values, just declaring column names. So the reason that we usually start with a standard scatter plot is to visually inspect the data for sanity. This scatter plot looks absolutely normal, and we can say that the vast majority of our points are around 14 and 15 threads running. At first glance, we don't need to do any data cleansing, but if we had a non-trivial amount of extreme outliers, you might want to figure out what is wrong with your data generation process or manually clean the outliers. Just do a log regression or percentiles or whatever you think is appropriate. So we ran the USL model against the same data set, and this is what came out. We can clearly see here that the trend line is not right. Everybody here knows that MySQL is absolutely not infinitely scalable. This is a common occurrence when doing capacity planning. In this case, we had so many thousands of data points between 14 and 16 that it overwhelmed the 10 data points outside the range. In capacity planning, the quality and usability of the data set you have is everything. In order to get a more usable data set, we took the maximum value of QPS for each thread's running entry so that threads running is a unique column in the CSV. Now our data looks a little cleaner, it's a little simpler. So we try again with our new data set, and the output looks a lot more readable. This is real data, so this really worked. Capacity planning, rarely done without cleaning data. In this case, it wasn't terribly difficult. In addition to the RUSL package, we wanted to show you how to use Barron's worksheet because it has some built-in normalization that is far more accommodating to the output you get out of a live MySQL server. I have spoken to some people at this conference, and they were like, yeah, we do capacity planning by spreadsheet, like, every once in a while. I'm not too proud to admit it that I love spreadsheets. Capacity planning spreadsheets are great, and Barron's spreadsheet applying the USL is so awesome, and it makes the USL magic. We took the data and pasted it into the concurrency and throughput columns of Barron's USL Excel worksheet. And we went with more of the raw data at this point in time. The default graph looks very off again, right? Like there's no real good trend line there. So it's off for the same exact reason the original one was off. We know from the scatter plot that we don't really have anything meaningful under 14. So we add 14 to the N offset and then take a look at the analysis tab again. And now the graph looks really good. And this, for the most part, reflected what it actually does in real life. Capacity planning is so much easier when you have good data. It is worth the time to fix whatever generates data so that you can save time down the road when doing capacity planning. I hope I've demonstrated how awesome the USL model is. And I'd like to just leave you with some verbose closing words. Know your SLA. Your SLA is your reference point for all things capacity related. Why? Because if you don't have an SLA, you have no idea what you're shooting for. There's no real point in capacity planning without it. If you don't have an SLA right now, take a stab at writing one. At a bare minimum, it should include your latency requirements and your uptime requirements. Second, learn how to do cost modeling. Capacity planning is only really interesting to other engineers. I cannot count the number of times where a formal capacity plan has been done and accurately predicted when a system fell off a cliff, only to have the engineering team watch it fail over in real time because there was no budget for real hardware. They didn't know how to make the argument. Cost modeling is often the phase that immediately follows capacity planning. Everyone in this room should know the cost it takes to provision a single customer on their platform. And you should know how, when you modify hardware and you add or remove servers, how that impacts that margin. Third, know your seasonality. Retail folks know the importance of Black Friday. Gambling sites know the importance of the World Cup. I see some GoDaddy folk in here who probably know the Super Bowl. If you have any recurring event or times that you require an exponential amount of extra capacity, know that Holt Winter's forecasting actually does allow you to take that into account. Fourth, international expansion can increase the complexity of your capacity planning efforts. I've heard engineers say that you can just at nighttime Europe will be up, and then during the day the U.S. will be up, right? So, but it doesn't always work like that. There's a lot of overlap in the active times, so it actually becomes there's a period of time between the end of the U.S. day and the beginning of the Europe day that you have to have extra capacity. And be realistic. If you're trying to shoot for 100 times capacity in every system, that's just not worth anybody's time or money for the most part. Focus on providing your value, prove your cost-benefit analysis, and then go ask for budget to implement it. And know that if you are having capacity problems, it's probably because you're making money, and so that's a good thing. Thank you for your time. Anybody have any questions? Cool. Nope, nothing? Thank you very much.